So in the previous example, we just looked at coefficients to set up a system of equations. That system was pretty easy to solve, no big deal. Here, the system is going to be a bit more of a pain, and so we're not going to work through all of that. We'll just see why it's a pain, then we'll take a look at a method to deal with that. But here, since we have three linear non-repeating factors in the denominator, in other words, there just aren't any exponents at all to deal with, that means I just need a constant over x plus 1, another constant over x minus 1, a third constant over x minus 2, and that needs to equal the original expression. And our job is just to figure out what those constants are. Here, I'm okay if you just put a little scribble there, because the rest of our work is going to make it clear what we mean by that scribble. So we need a common denominator on the left. The first one, it already has the x plus 1, so it needs an x minus 1 and an x minus 2. I'll put that in the numerator and in the denominator so that I'm not actually changing anything, just multiplying by 1. And I'll do the same with the other two fractions. I'm just going to do that in my head. So the a needs an x minus 1 and an x minus 2. That middle term already has the x minus 1. It needs an x plus 1 and an x minus 2. C already has the x minus 2, so it needs the x plus 1 and the x minus 1. That's our numerator. It's all over that common denominator with our three pieces multiplied together. And it needs to equal our original. Again, with those same three pieces multiplied together. As before, if the denominators are identical, then the numerators need to be equal as well. But the issue here is that we have three terms to worry about coefficients. I have an x squared term, I have an x term, and a constant term. And that on its own doesn't automatically make this terrible. There's something else that we'll start to see that makes it a little bit worse. But the coefficient for x squared needs to be 2. For x needs to be negative 13, and all of our constants need to work out to be 3, based on what the right-hand side says. Where this gets difficult is finding those coefficients on the left. And it's mathematically not super difficult, it's just annoying, and we would rather not do it. We would need to multiply these two out, and then distribute the a, and multiply these two out and distribute the b, and multiply those two out and distribute the c, and then combine like terms and look for your x squareds and your x's and your constants. It's doable, you certainly have the skills to do that, but it's kind of annoying just for that, and you then end up with a 3-equation system, which in many cases is significantly more difficult to solve than just a 2-equation system. So long story short, we're not going to bother with that. We are going to take a look at a different method. Here, what I'm going to do, the work we've already done was not for nothing. I'm going to take exactly what we had before we decided not to continue with this method. I'm going to take that and just copy it onto the next, and we'll take a look at the Heaviside method. So I have the a, x minus 1, x minus 2. See if I can remember that. There's Heaviside. His head is weird. It creeps me out. But that's okay. Bonk. So let me copy what we had. We had an a, x minus 1, x minus 2, and then a b with an x plus 1, x minus 2, and then a c with an x plus 1, x minus 1, and that needs to equal our numerator 2x squared minus 13x plus 3. What the Heaviside method has us do, and it is brilliant and super awesome, is to say if these two expressions are supposed to be equal or equivalent, then they need to be the same for any value of x we want to plug in. So what this method has us do is just to plug in kind of convenient or just smart values of x, and you'll end up with a really simple thing to solve. When we talk about smart values of x, it's really just a value that makes one or more of those terms turn out to be 0. So for example, one convenient or smart value of x would be x equals 1. because when I plug that in, I have a times 1 minus 1, and that's why this is good. 1 minus 2, b gets a 1 plus 1 and a 1 minus 2, c gets a 1 plus 1 and a 1 minus 1. And that equals 2 times, plugging in 1 on both sides, 1 squared, minus 13 times 1, plus 3. So here, the reason that that was great is that now the term that had an a in it is gone, because there was a 0 in there. The term that has a b is still there, but the c, there was a 0 in there as well, so that's gone too. So what we really have is just b times 2 times negative 1, so b times negative 2, equals 2 minus 13 plus 3, which as usual I am too dumb to figure out, negative 8. There we go. And then you have a really simple thing. B times negative 2 equals negative 8, and b equals 4. Okay. Take just a moment, pause me if you need to think about two other convenient values of x. We've plugged in x equals 1 as one of our convenient choices or smart choices. There are two others we want to plug in. Think about what they are. You could even go ahead and plug them in if you wanted to. And so looking at this, another smart choice is x equals 2, because that's going to make this x minus 2 turn into a 0. It's also going to make that x minus 2 turn into a 0. So to save myself a little bit of writing compared to what we did before, I know that the a term is going to disappear. You don't even have to write that much. I know the b term is going to disappear because that 2 minus 2 makes that term a 0. My last term is a c. 2 plus 1 is 3, or something resembling a 3. 2 minus 1, last I checked, is 1. And then over here I have 2 times 2 squared minus 13 times 2 plus 3. So the left side, super simple. C times 3. The right-hand side, 8 minus 26 plus 3, which is 11 minus 26, which is negative 15. And so C is negative 5. Okay, so that was our second smart choice of x. And then our final smart choice of x, we've used a positive one because that took care of this term and that term, or that part of that term. We've used the x equals 2, so now the only clever choice of x that remains makes these terms 0, and that's x equals negative 1. So I have a times negative 1 minus 1, negative 2, negative 1 minus 2, negative 3. The next term becomes a b times 0, so it doesn't matter. Then a c times a 0, so it doesn't matter. That was the whole purpose of choosing x equals negative 1. The right-hand side, 2 times negative 1 squared minus 13 times negative 1 plus 3. So here I am left with the left side, very simple, 6a, so simple, you might do it wrong, 6a, and then the right-hand side, 2 plus 13 plus 3, 18. 6a equals 18, so a equals 3. Our final step here, we've done most of the hard work. In fact, we've done all of the hard work. We've plugged in 3 convenient values of x. We have found our 3 constants, a and b and c. So all we need to do is put those back in our original. On the previous screen, I wrote out what was going where, but as I recall, my a was over the x plus 1. My b was over the x minus 1, except now I know what b is. It is 4. And my c, I usually do a plus down here and then the negative up there. Of course it doesn't matter, but that was over my x minus 2. That is our partial fraction decomposition of that expression. And so, once again, if I asked you to integrate this, that would suck. But if I asked you to integrate each of these, that's not bad at all. And so just recognizing that those are equivalent is the whole purpose of the algebra behind this section. Here again, I'm going to move on to a new video before I move on to the next question. So I'll see you back here.